this experiment, I will explain about introduction, learning outcomes, and additional theory.
My name is Muhammad Rahman, and my number metric is AA190 and 763. And today I will explain to you about objective, apparatus, and observation for this experiment.
Assalamualaikum and hi. My name is Muhammad Haikal bin Abdul Rahman, matrix number AA190872 from section 2 Material Science. For this experiment, I will explain about procedure and result.
Assalamualaikum and hello. My name is Muhammad Hafizuddin Binodin. My number matrix is AA191510, and today I will explain to you guys about discussion and conclusion.
This is the introduction for Haredenability Test. The influence of alloy composition on the ability of a steel alloy to transform a martensite for a particular quenching treatment is related to a parameter called hardenability. Martensite is a hard and brittle microstructure. The hardness of a steel refers to its ability to resist deformation when a load is applied, whereas hardenability refers to its ability to be hardened to a particular depth under a particular set of conditions. Hardenability determines the depth and the distribution of hardness induced by quenching from the austenitic condition. After the sample has been austenized, it will be quenched in different quenching medium, which are water, brine, solution, or oil. This property is important to machine component and tool steel. When quenching big steel component, normally the hardness at the center will be lower because the formation of ferrite and pearlite. Instead, its surface has high hardness. The difference on hardness at the center and surface may be explained by continuous cooling transformation or CCT of the steel. If the cooling rate does not cross the transformation curve, it will produce the same hardness of those whole steel. In this experiment, we will learn about how to conduct the hardness test under constant load on given materials and present the collected data in terms of hardness versus distance from quench and describes the curve. So this is the additional theory for the experiment. The hardenability of steel is defined as that property that determines the depth and distribution of hardness induced by quenching from the austenitic condition. The factors that affect the hardenability of steel are: first, composition of steel; second, austenitic grain size; and lastly, structure of steel before quenching. Hardenability increase with carbon content and with alloy content. The most important factor influencing the maximum hardness that can be obtained is the mass and the metal being quenched. Hardenability of all steel is directly related to a critical cooling rates. This is taken from the first reference.
My name is Muhammad Shazwan bin Abdul Rahman, and my number matrix is AA190 and 763. So today I will explain to you about the objective, apparatus, and observation for the experiment 2. So for the objective, which is first, to understanding the relationship between the hardness of the cooling rate of the specimen after being heated using the Jomini test method. Second, by using this Jomini test, we can determine metal hardenability. Third, this experiment is aimed at understanding the effect of cooling rate on the hardness of the steels. So next we go to the apparatus. So how we want to conduct this experiment too? So we will conduct this experiment too using this machine, which is Gemini test machine. So what is Gemini test machine? The Gemini test machine is an end quench test issued to measure the hardenability of a steel, which is measure of the capacity of the steel to harden in depth under a given set of conditions. This TLP considers the basic concepts of hardenability and the Gemini test.
My name is Muhammad Haikal. I will explain about the procedure. Firstly, preheat the furnace to 900 degrees Celsius. After that, in 1 hour, place the Gemini specimen in the furnace and socket. Turn on the water in the Gemini sink. Next, adjust the free water column to about 2.5 inch. Rotate the baffle plate to block the water column until there is no contact between the water and the test specimen. Then, remove the Gemini specimen from the furnace and put in the fixture. After that, remove the Gemini specimen from the fixture and grind evenly on the side of the specimen. Next, perform readings at intervals of 1 mm to 10 mm by measuring Rockwell hardness. Repeat step 8 with an interval of 5 mm to 50 mm and an interval of 10 mm to 100 mm. Plot the data for Rockwell hardness versus distance form. Now, I will explain the result of the experiment. When the distance quench is 0 mm, the hardness is 55.4. Number 2, when the distance quench is 3 mm, the hardness is 54.7. Number 3, when the distance quench is 6 mm, the hardness is 53.4. Number 4, when the distance quench is 9 mm, the hardness is 52.6. Number 5, when the distance quench is 12 mm, the hardness is 57.3. Number 6, when the distance quench is 15 mm, the hardness is 47.7. Number 7, when the distance quench is 18 mm, the hardness is 46.2. Number 8, when the distance quench is 21 mm, the hardness is 44.0. Number 9, when the distance quench is 24 mm, the hardness is 43.7. And number 10, when the distance quench is 27 mm, the hardness is 41.8.
So next, we go to the observations. So based on the experiment that we conduct, the observation that we saw is first, the cooling rate varies throughout the length at the bar, the rate being the highest at the lower end, which is in direct contact with water. Second, the hardness along the length of the bar is then measured of various distance from quench end and plotted in a graph. Thirdly, the greater the depth to which the harden penetrates, the greater the hardenability of the alloy. Fourth, hardenability ensured because of the cooling rate decreases as one moves further from the quench end. We can measure the effects of a wide range of cooling rates from very rapid at the quench end to air cool at the far end. Lastly, by comparing the curve resulting from end quench tests of different grades of steels, their relative hardenability can be established. Thus, flatter the curve, the greater the hardenability. That's all from me. Thank you.
Hello, my name is Muhammad Hafizuddin and I now will explain about discussion. The hardness of specimen depends on the distance from the quench end, as can be seen from the hardenability of the plotting. Beaker's hardness decrease in line with the distance from the quench end. However, we can assume that the hardness of beaker is high, as the value of the hardness measure decrease linearly in low value on the basis of the pilot if the distance from the end quench of the beaker bigger. The hardenability of the beaker would become weaker arsenic occur at a range of 0 to 3 mm. Martensit and perlite exists on the distance between 3 mm and 9 mm. Otherwise, we expect fine perlite to be in range between 9 mm and 15 mm. Finally, we agree that perlite exists between 15 mm and 27 mm. So for the next one, water quencher is faster but makes the metal brittle. Our stress is started due to rapid cooling, while oil quencher cool the metal slowly, which release stress and keep hardness in check so that the metal perform at high stress. Heat extract much faster when use water as a quenching, while oil as a medium has an opposite effect. This is because the thermal conductivity of water is higher than the most oil. We could observe that water cooling typically will have higher hardness and more stresses, but when using oil cooling system, it will generate lesser stress and moderate hardness. The water also have lower viscosity compared to oil, and density of water is higher than regular oils. Last but not least, water convection coefficient higher compared to oil. Thus, this make water has a better quench or efficiency. There are several factors that influence hardenability curve. Firstly, transforming of arsenic when heat treating. Still require that the component be heated into the arsenic phase range. This makes gradual quenching while retaining hardness for decreased distortion. Then the calculation of hardenability also affect the hardenability curve. The desired diameter of provided steel to harden to 50% of the martensit when quenched in a bath where H is equal to infinity. This is the hypothetical infinite cooling rate that is equivalent to instantly reducing the surface temperature of the steel bar to the quenched temperature. So, in conclusion, the Germany test defines the capacity of the steel by quenching to be hardened in detail. Hardenability depends on the steel alloy composition and can also be influenced by manufacture, such as the temperature of austenitization. In order to choose the required combination of oil and heat treatment for components of different size in order to reduce thermal stress and distortion, knowledge of the hardenability of steel is important. Several authors who have investigated the effect of deviation from the standard test produced have included that the most important factor to be closely controlled are austenitization temperature, time grinding of the flats of the test bar preventing of grinding burn, and accuracy measured distance from the quench end. Other variables such as water temperature, orifice, surface diameter, free water jet height, and transfer time from the furnace to the quenching fixture are not as critical as like we stated before. Okay, that's all from us. So this is our reference. Okay, thank you.